Tā, cerams, ka jūs man dzirdat. Šoreiz esmu uzlicis AI, tikai to tur trokšņu noņēmēju. Īstenībā AI trokšņu noņēmējs arī strādā uz laika rindu modeļiem. Oh, sorry. Sorry. So I'm a little bit sick. Sorry for that. I forgot that we are doing this in English. So today I set up the AI noise reduction model and the well, speech enhancer model. So we'll have if I'm a little bit coughing, so then you will not hear it. Okay, so let's wait a little bit for more people. Hopefully, um, at least in the homework section, I saw quite a few submissions for the homeworks. It was not like it wasn't it doesn't did not look that a lot of people have given up, which is good sign. There's still quite a few people who have finished the homework, so thank you for that. Also, yeah, so just let's wait a little bit and then start. Let's give it 3-5 minutes, okay? Maybe meanwhile you could check in the chat. So can you see and hear? Okay. Plus minus any problems? Let me know in the chat, and we'll start shortly. Okay, so yeah, I see. Thank you, Malta. So then, okay, we'll see. Hopefully, others will check with this lecture later. The I think the kind of the main reason why we do this live is that we can ask things, and we also can review previous work. And the best is of course to do this in person, but otherwise this is better than just a video. So here I just want to make give like so that you understand that this is important. So inside the Moodle, if you go down to the voting here, I see that not everybody has voted. Only the uh, LIEPA ISRTU have voted, right, for the exam dates. Keep in mind that I will give just one exam date for each location, so it will not be able to come many times to these locations. But please vote for these locations, okay? So that we have agreement when we will do the paper exam, or maybe it will not be paper. Maybe I will just use one of my AI agent systems where I can give you questions, but it will be basically the ABCD questions, and maybe I will give also some analytical task where you describe how you would solve the situation using tools that you now know. So now we are at the stage where we are looking at the recurrent neural networks, LSTM, time series models, and so on. But before that, let's just review a little bit the homework. Okay. Sorry. Hopefully my denoiser is working. We'll see. So okay. So regarding the homework, I will try to make this in one section. I know there were a couple of tasks. Really happy to see that many of you actually managed to get also to the last task. And really happy to see that many of you pay attention and submit also the screenshots of running code, because of course I can look at the code and see quite fast if it will be running or not, but still it is better than that you produce some kind of real output so I can evaluate it instead of I need to run every single code and check it in that way. So let's do this code review and a little bit analyze what we have. So we had the homework of doing the dice loss function, and it says that you should add this dice loss to previous part of the work, which I think we added. We added the fully connected layer, and then the IOU, intersection of union metric, which is very popular in these segmentation scenarios. And just for you to interpret these metrics, we already see some maybe interesting stuff here. Basically, first of all, remember that right. So just let me see. Can I add text more easily? We'll see. So yeah, next time I will use FigJam for presentation, not Canva. So the y is actually always the values either 0 or 1. So yeah, basically from 0 till the y is actually 0 or 1, and the y prim is basically in between 0 and 1, right? So, and if this is the situation, and this I mean y for every pixel, right? So each pixel have these ranges, right? Not, yeah, so so this is not just a one-dimensional array, right? This is a multi-dimensional array. For each class of objects, we always have 0 and 1. Just for you to remind a little bit visually, if you've forgotten what I'm talking about, but I believe those of you who submitted the homework do remember this, but still, let's find that picture. Add it somewhere. So where's the units? Okay, cool. I have it. So there was basically this one. I think this is good. So the idea that the input pixels have 3 dimensions and the output pixels have these basically right, it's not actually that great because it's this here, it is the persons are 1, the bench is 1, and then for some weird reason, or maybe these are ones because I just don't see them, but anyway. So what I'm trying to show you here is that so do I have some drawing tool, right? So that these each pixel have this 0 to 1 range for the prediction, and for the real ground truth mask there is always either 0 or 1, and this is built in these channel dimensions. So this is the channel dimension, right? There are 4 channels, 4 types of objects that we want to detect, and the inputs are in this case RGB, right? The 3 dimensions, right? So that's what we have. And why I'm pointing towards this is because if you look at this equation, you can easily emulate this in your own brain. Like if there is this is like basically 0 times 0, it is 0, right? And if it's 1 times 1, then it's 1, and then it's divided here by the real values and predicted values, right? So basically, it should. So let me check. So I think it should go. Dice loss should go towards 0, I believe. So let me see. Let me double check. So if that one is, so it will divide it by. So if that side is 1, so everything is perfect basically. So if this side is 1, everything is perfect. So then there would be 0 basically. And sum of parts of this equation is actually very similar to IOU. So here on the IOU, we also have this Hammond product. So basically, for you to know, sometimes in scientific publications you write it like this or you write it like this. This is the same thing basically. So this means pairwise multiplication, right? So if you see any time these kind of formats, this means pairwise multiplication basically, or Hammond product they also call it. So pairwise multiplication, okay, not dot product. Okay, cool. That's that. So the metric and the dice loss, which can be actually added to other losses, like cross entropy loss can be added to the dice loss. It doesn't need to be just that one. Okay, so that's that. Let's look at the actual works. So here, let's just review a little bit. So they actually have quite a few images. So I like actually this one because it seemed that the person tried to combine the IOU with the other metrics, which is fine. But the best way how to do this would be to split the plot. But let's see. Okay, so let's go a little bit into the work. Probably will not have time to evaluate every single piece together, but let's look at that. So unit. So fully connected in the middle. Let's see if that is the case actually. Is this really the fully connected? So maybe that is a misunderstanding here because there should be here fully connected model. So not fully convolutional, which is so basically this is funny. FCN, it is the same kind of like the letters. So fully convolutional model network, right? Network and then FC also means fully connected. So, and these are two diametrically opposite things. So, because from what I see here, actually I don't see linear layer anywhere. So, the fully connected means linear layer basically. So, let's look if anyone else actually implemented this. I did not open all of the homeworks, by the way. If I don't show your homework, sorry for that, because like, of course, we cannot go through everyone. I just pick randomly some. So let me add this a little bit to the notice. So we need actually that, and we'll see if anyone has implemented this. So we'll see. So it's not actually fully convolutional network which we need. So let's look. So there is another implementation, and I see here person made dice loss and also the IOU metric. But what about the other parts? So, okay, somebody tried to implement unit plus plus, but it doesn't look at all unit plus plus. So this code is very strange. So it definitely not unit plus plus, and also yeah. So this looks really not that good. But maybe if it's just like a dummy placement, maybe we should just look at those equations. We will look at that as well. So there is another implementation giving such a chart. Only I have seen this chart I think before. Yeah. So I don't like this at all. If you just share your code between your colleagues, this is basically also useless. I sometimes give just 0 points for doing this because you see, like it's easy to see that this is exactly the same person do code because like if you this would be different code, you would not use exactly the same everything, right? So basically, this is not good at all. Probably I will have to remove points for that, unfortunately. So please don't do it. Like it's pointless just giving the same code to your colleagues. So here, let's look at this implementation. So conv middle. Also, I don't see fully connected here. This is also not right. If you have comments right in the chat, I can address that as well. Res block unit again, no implementation in between. So actually here, right, there's nothing here. Let's look at this one again. Seems very same code as before. Really bad idea for you to share code with your colleagues, because this is exactly the same wrong code copied twice. So I will, like, this is useless. So if you keep doing that, you might as well not do that. Please do not do this. So you cannot learn anything if you just like copy or generate code without any understanding, right? So unfortunately, nobody of you, at least I don't see anyone, implemented the fully connected layer in between, which is strange. Maybe you did not understand that you need to keep advancing the same model. If you do that, then let me know in the chat. But let me explain how this could be done, okay? So I will not run the same code right now just because of the time constraints, right? But I will just explain how this should work. So let's see. So if I have these res blocks and we are now getting this to the 64 by 64, and we initially reduced the dimensionality probably, right? Um, we do the max pools. Okay, cool. So how this could work actually. So one way, so we could just add here FC middle. This will be torch and linear layer in feature 64, and depending on how I want to implement it, I could just add 64 out. So this would be the basis, not the con. And then here, how I would address this, I would make the, so I cannot make sure, I need to make sure that this is one by one. So how to do that? So this will be, right, so this will be out one by one, and how to get that would be torch, or maybe I already have F, yes, adaptive average pooling over 2 dimensions. So the skip for output size I want to be one by one. I need to also save the input size. So uh, this will be the, because I will need to restore it in size f adaptive average pooling. Oh, no, sorry, skip skip size. So the first 0 dimension is batch, right? Batch channel height width, normally like that. So then this would be, in this case, it would be something along 0, 1, 2, because these are squares, so this will be okay. And then the next step will be out flat, where I will flatten this thing. View -1 64. So the 64 dimensions by batch. -1 is good because in inference, when I have batch size 1, it will still keep working. So that's that. And then the out FC will be self FC middle forward out flat. And then I need to restore the same dimensionality. I will do the, again, out one by one. Sorry for my coughing. I hope my noise reduction works. If not, sorry for that. So this will be one by one. And then finally, I will need to get it up the same size as it was in the beginning. If adaptive average pool, I can do the other way around as well. Out, or I can upscale actually. It doesn't matter which function I use here. Um, so I'm not sure. Actually, adaptive average pooling might not work that well, but there's adaptive upscaling. Do I have it? Let's see, upscale, upsample. We have with the upsample, scale, factor, size. Yeah, I think the size should work basically. So out one and size, and here this would be the in size, comma in size, something along these lines. So this is not actually perfect implementation because the perfect implementation would not use adaptive average pooling. I would reduce the size to 1 by 1 normally with convolutions and then execute the fully connected layer in between, and then this would be the situation where the model will learn not to recognize objects which are separated. So remember, like from the parts, basically. So this would be the better implementation, basically. And the so the why we are doing this, let me see. So here, this was the comment I made last time, that we want to avoid this kind of situation because the code on the left basically, so let me draw. So with this code you might have a situation like that, and with this code this will work like that. But and so it will both will find faces in the image, but one, if there is a like some parts of the face, also will find face. So the fully connected layer helps to avoid these situations. So that's why you need to know how to build them. Yeah, so I just want to add myself a reminder that I need to finally solve the situation with homeworks being played, basically, because please, like, I really very annoyed about seeing homeworks like these, basically. Where was it? Like this one is super annoying. Please don't do this. Like, especially you submit multiple times the same homework from different people and do it in the wrong way. So this is definitely not what I want. So homework grading issues. So I will address that. So, and by the way, if you cannot follow this course, remember there is another course, the business course, where basically you can go and learn AI on much easier level. But if you want to learn it in proper level, then try to do yourself the work, not just copy from the others. Like that's no use. Okay, so let's keep looking at the other parts. So that was one. The other one, so the loss. Okay, so this is also okay. As you saw, some of the quote unquote genius people who generated code use basically something like this, or it looks even copied from some material out, like from GitHub or whatever. So you can do this as well, of course, make a special module and then use the module as a forward pass, right? Actually, let's see if this so yeah, something like that. Or you can write the loss function like this person did. So I believe that this person actually, it looks like this is more code that is written by themselves. You see, there's it looks actually that there is some changes done. So this is then let's look torch sum. Yeah, so this is the simple multiplication, and this is only possible when the both matrices are the same size. In this case, these are the ground truth matrices and the predicted matrices, so they are the same size. The only, so let me think if there should be numerical stability here. Can you break it down? Can you basically divide it by 0? Probably not, except it might be actually. So it might be situation that that in the batch that you're working with, there is no samples with with particular class basically, and then it will be division by 0 basically. So what you can do, normally you would add here plus e minus 8, which is the smallest, no, e minus 16, no, no, e minus 8, which is the smallest 16-bit float, I think. And if you want, you can also add it in top, and then it would be a smoothing function basically. But in my experience, it doesn't matter that much. But you can do it either in that way or that way. But just to add it so that we don't have the division by 0, right? Because in some batches might be long pictures without the markings, right? So that's that. Oh, yeah, but please stop doing that about the copying other people work. So it just makes headaches for me because then I need to implement myself a script to find the same code, which I can do easily, and also headaches for everyone. Like this is like no use. So then also sometimes loss functions can be combined. Hopefully you understood that already. Normally in these solutions, actually you would do something like this. You have the like BCE loss plus the other loss, and the other loss, like even the BCE loss could have some coefficient like C BCE, and this coefficient will tell how strong should I prefer this part of the loss function rather than other part. So that's something that also can be used. And then IOU. So I like this implementation because this implementation seems readable, and also that I see that the person most likely did it themselves instead of copied from somewhere. So also the smoothing function, the true positives where the both match, false positives. So let's see about false positives. So false positives mean where the both don't match. Basically, sure about that implementation. And false negatives. So let me look at what was the original equation. Maybe it is right. So the original equation. Right, so we have this one. True positives, right? Yeah, it is the same. Yeah. Yep, and then there is a false positive. So yeah, nice. I think this is good. Yeah, I like it. And then the only thing is how it's plotted. Right now it's plotted in the same part. I appreciate this person actually doing this. I need to, so I just want to make notes myself that I should give points to this person more because I see that this is actually has done pretty well, except the fully connected layer. Uh, I don't know, you know who you are, but this looks good. And then here the IOU. How did you add the IOU? I like that you added it there. So append metrics. So this shows that the person understood the code quite well. So this is really nice. This is very good sign. Metrics. So it goes to the metrics. Where is the subplot? Grace. Okay, here's the thing. Right. So my only advice here would be right. So we have these. Now there is the train test IOU. And what we could do here, we could just create some subplots. If you see there is a subplots basically make, in this case, I want to have one row, two columns, and the first index is where I'm looking at right now. So what you could do here is like change this part of the code uh, to basically create even maybe two subplots here. So what you could do is something like this. You could have two rows to one column like that, two columns, two rows, and here there would be the second row of the first column basically. So this would be two. And here we can just add something along lines like this. So if if key, so if IOU IO IOU in key, right? Then we show, and then I just copy all of this stuff again, and there would be, okay, I just also that one, and there would be IOU not in key, right? And then you will have two nice plots, basically, not jumbled together in one axis. So this is something to explore yourself as well. Okay, so let's stop about these things, but again, uh, reminder, please don't copy code from colleagues or generate code that is useless for everyone. And I immediately see that that's not like a genius way to generate code and nobody sees it. It's super obvious, basically. So that's that. Then let's keep moving to the today's lecture. So today's lecture. Oh wait, I will look at chat maybe. Maybe we have, right. So somebody is here at least. Okay, cool. So today's lecture. Sorry for my cough. And hopefully the voice remover works. The noise remover. Okay, cool. So we will talk about the recurrent neural networks. Recurrent neural networks are very cool. I just want to make sure that I give you the right reference, but right now there is still RNN architecture, which is on the same level as the transformers, and transformers will be something I will show you next week. So let me double check about next week actually, when we can do this. So next week I will try to shift the lectures so to the day, basically before or after Christmas, so that you can join. Okay, because the transformers are super important. Transformer architecture right now is the same architecture that's using by ChatGPT, right? So on same accuracy as transformer. So I just want to give you the reference and you can then explore it later. There is one RNN architecture that is working as good as transformers. Right. For some reason I cannot find my note, but okay, I will do that later. Let's talk about these recurrent neural networks, and then at some point I will try to find the name of the model, which is very powerful nowadays. So the how this works. So this is just a very simple equation in the simple implementation. This is vanilla RNN. So basically, usually it's actually called like that. But we will do also not vanilla. We will do something which is more powerful as well. So vanilla RNN. And vanilla RNN is basically some of the main things you must notice here is that inputs, like we have a time series, and let's visualize it more. I will give you some more visuals. What are these inputs? So these inputs can be, of course, anything, but in we could think them as, for example, sensor readings, right? So we have some sensor readings, and the time is on the x-axis, the y is the sensor reading, right? And if I feed the sensor reading inside my model, step by step, the time 1, time 2, time 3, at some moment I can start predicting the next sensor readings. Or I can do actually classification of the whole sequence, or do the other things. So, and the idea here is this, that what you can actually do, and this is not wrong, many things that you can do in these deep learning models, they are not wrong. You can use your creativity and think of clever ways how to operate. But I just want to show you that basically you can imagine that if you have a 1D convolution, right? Just a one-dimensional convolution. We talked about two-dimensional convolutions with kernels, right? So if I have 1D convolution, and you can do that, conv 1D, yeah? And let's say the kernel is kernel will be some 5 time steps, right? I could actually do this convolution, and I could with the stride like cover all of this time series, right? And then I could build a model that predicts some outputs. And this is okay, basically. This is one approach how to do this. But one thing you already see that the same kernel convolution is applied to different time steps, right? Many times, and then you have the prediction. So this is one way how to do this. The other way is the proper way, which is this vanilla RNN, where we have memory, and the memory here is the, so let's color something. So this will be the memory h vector, and by the way, in the very beginning, the memory is usually set up as 0. So this is the memory vector, and we pass the same uh, so h we pass the same weights multiple times for each time step. This is very critical because sometimes people do not get it immediately. So what I'm trying to tell, that for each time step there is no different weight. So for example, for time step 1 there is no specific time step weight for 1, like or kernel for 1. That is the same kernel function, basically the same weights apply for the every single time step that is coming in, and also for time steps that will be coming out. So the idea is that we accumulate gradient over time. So, and this is called backpropagation through time, basically. The idea is that what I'm doing here, I'm first on the downside here, I'm projecting my inputs using the weights of x. Then I'm plusing it with the projected memory inputs, and I'm biasing it, and I'm passing to the tan h function. And here is one trick you must notice here, that tan h is coming from -1 to 1, right? So the tan h is -1 to 1. But if you notice that the equation actually have this, so there is a -1 to 1, it has this plus sign, right? So the idea is here that you either subtract something from memory or you add something to the memory. Basically, that's the main idea here. And you backtrack through the time. And here, this is super important why we implemented in many implementations this thing. So optimizer zero grad, because so this is one function you must know. So you, if you have worked with the homeworks, you know this is such a function there. And before, when we implemented NumPy version of neural networks, we always had something like this. So self weight grad plus, so there will be d of the loss of with regards of weight, for example, something like that. And this is a key here, because this is super important for recurrent neural networks, is that we don't just add gradients to all of our weights when we do the back propagation just once. We actually do it many times, because you see the same orange weight is in different time steps. And also cool that the lengths of sequences can be arbitrary. It can be as like it can be any length of sensor readings and any length of sensor predictions. This is super powerful because the transformer architectures, which are right now the state of the art primarily, they are not only option, but they are primarily state of the art. They are very limited with length. So if you look at ChatGPT and all of these language models, they actually have limited length of text that they are able to process with high quality. But with the recurrent neural networks, there is potential to have processing much longer sequences. In practice, actually, it doesn't work that well in many cases, but there is still this potential. So I want to show you more couple of things before we jump into the code. So And if you have any questions so far, please let me know. So there will be, first thing to understand, we will have a for loop basically. So there will be a for loop, but don't worry, like in professional PyTorch implementations where you will use Torch NN, LSTM, GRU, and so on, this for loop is implemented actually in the CUDA level, in the GPU level, so that this will be executed much faster than just Python for loop. But still, nonetheless, we have the for loop because every next prediction is dependent on the previous prediction. So this kind of model is not as good as convolutional model in sense of performance because you always have wait to the next sequence. Because for example, if I want to predict these guys, I need to first process all of these three, and only then I can start predicting the next ones. So, but if I'm using the image recognition with convolutions, I can do all of the pixels in parallel, right? So there are some disadvantages. So what we need to notice about these schemas, so all of them can be implemented with recurrent neural networks. You can do any of these combinations, and you can train them also with any of these combinations. But there are some things to notice. So let's look at something. So for example, if I have inputs the red, outputs the blue. If I'm trying now to train my model, so let's see. So maybe this case, this is typical. Maybe I should also put some visualization. I had more. I think I had more. So let's look at another visualization. More visualizations helps to understand the problem better. So if I have something like this, so the number of trips, days, predicted training input, training output, right, and sliding window, and we are predicting this. And by the way, we could actually have not sliding window, but because we are still training on batches, so each batch will have some part of the data, right? So then we still have sliding window because we cannot just get around by feeding the whole dataset in one go. Usually datasets are very large, and probably this will not actually work very well, as you will see in a second. So normally, what is the shape? It will be batch, sequence, features, basically. And features, actually, if you're talking about video, so let me show you how the video would look like. Video will look like batch channels with height or height width, basically usually like that. So this is a common way of the basically the inputs. And there is also, you will see in the code, there is one trick that everybody uses. The trick is that because if I want to do the for loop and I will work on for loop with batch and features together, then it's often smarter to move sequence in front, basically. So that's something that often people do. And these models have always the parameter is sequence in the first dimension or the second dimension because for loop makes it easier to work if this is in the first dimension. So to return to the point, so the why and how to train these things is, so I have the inputs, I have the outputs, and I have the loss function, and it says that let's check that if this one output is correct. So how the gradient will go? The gradient will go something like this. So it will do the chain rule, back, 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 and it will go to this sample like this, and then it will do the same for this sample, and then for like for every single sample it will go the back propagation through time basically. The problem with this is like if you have longer sequence, you can imagine that if there is no skip connections, and there is no skip connections here as you see, then what will happen is that the gradient will become smaller, smaller, smaller until it will be vanishing gradient basically. So you don't want to train it like this, never, like almost never. You don't want to train it also most likely like this. You definitely don't want to train it like that. And if you train it like this, it will be quite useless because there is no use of recurrence actually here. So the only way how you train it is actually like this. So to understand that you always train your models in this way. So you will have the directly input, directly output, directly input, directly output, if possible. Sometimes it's actually not possible. Sometimes you only have one output for long sequence, then you train with other ways. But so this is for the training. And if you have trained your model, then you can use it in any other way. So you in the inference, you can use it in these other configurations as well. So inference. And if the model is trained correctly, it should work quite nice also in all of these other settings basically. So this is how usually it is done, right? Um, Let me check in the chat if maybe some questions or comments. Okay, not so much right now. Okay, let's keep moving. Okay, so this is the RNN basics so far. Before the code, I just want to share more things. So the practical task, what we want to do here. Right. Let's give the practical task, and then I need to come back to more things. So the practical task which I want to achieve here is the modeling of language. Language modeling is the same thing as you can imagine the large language models do. Basically, it is unsupervised method. So basically, we don't have some specific labels or humans working on the text. So you have some input text and some output token basically. And if you remember the coding of these words, right? This is something that we always use the embedding matrices, right? Or some one hot encoded embeddings, right? So for each word we have these kind of implementations. So let me show you. So for example, one hot encoded would look like something like this, right? So these are actually they call them tokens. Tokens are usually when you split word in separate subdivisions, right? But sometimes the whole word can be token actually, and you want to make sure that that you actually use the embeddings. So this is another way how to do this. You would have this one hot encoded vector multiply dot product or just selection. Usually, remember that in 99% of cases there is no use of doing this dot product. You can just select index of the third column here, and you would get the correct embedding, right? So these are the representations of the words. We have the inputs and we have the outputs. And what you do, you actually, in the language modeling task, when the model is finished, you feed the model with what the model has created. So what is the problem? Yeah, what then the predicted word is, then you can feed back the is, then the predicted word is there, then you feed back the there, then there's problem, and so on. This is how you could use it at the end, right? When you train it, you just need to shift a little bit the label. So you have a sentence here, what is the problem? And here what you do, you just delete the first word and shift it to that side. So this is how you can train it easily. It's quite easy to train, okay? So, and the dataset which I will give you is the quotes dataset from famous people from Kaggle. And if you look at the quotes datasets inputs, so you will see these histograms. First of all of the meaningless words are exponentially more common. And then if the word becomes more informational dense, these words become less common basically. So all of the words like architecture, mixtures, whatever, they are less common. And by the way, that is expected. That is not something wrong with the dataset. It is known phenomena. If you look at the linguistics, there is a thing called zip flow, where all of the small words in the languages are exponentially more common than the meaningful words in languages. But so it just means one thing. So why this is important it is super important that we add the weighted loss. So if I will not add the weighted loss, then my quotes generator will just generate always the da and and so on, right? So this will be my output if I will not take care of class imbalance, because here is a heavy class imbalance in language tasks. So language tasks should be taken with care, especially because there is this heavy class imbalance, right? So I just want to show you, so what is the loss function? And this will be the one version. Probably we should use some better version actually, because the weights here are not optimal. So this is the, okay, why it's not copying? Okay, right, could not copy some files. What is that about? So let's see, try to do this again. Okay, okay, it's copying. So this would be the weighted loss function. Do we have it here? Actually, C. Yeah, so C is the weight coefficient. And here the idea is that like if the word is more common, then it will have a lower C value. If the word is less common, you will have higher C value. But this is not the only way how you can do the weights. There is many ways. You can do the weights in other, like I think we talked about that already. So that is that part, and then finally the last thing before we jump to the code, I want to show you one thing to understand is that sentences in these datasets are not the same size, but I cannot put in memory, in GPU memory, uneven size sentences. I need everything to put in matrix, okay? So it means that we will definitely need to pad with zeros our sequences, and I will show you there are some PyTorch built-in functions to do this. And also keep in mind that there is an order, so that you start by the longest sequence and then you go to the shortest sequence. And why is that? This is because we are using for loop. And if you imagine that for loop goes through whole batch samples. So actually, let me find some, where's my, okay, these things. So if I have for loop over sequence dimension, for so for each batch, basically. So the idea here would be that the batch is these six sentences. So this is batch one. So sorry, yeah. So batch is the six sentences. Yeah, but this is the step one, x1, x2, x3, and then the batch becomes smaller and smaller and smaller and so on. So the idea is that you optimally want to have the same size sentences, but if you cannot do this, then you need to order them in this way so that you can process it with for loop. So there would be x1 with batch size 6, x2 with batch size 6, and then x3 with batch size 5. And you can track all of this and just execute mathematical operations on the size that you need, basically. So not more. Hopefully that makes sense, at least I hope. Yeah. Okay, so that's that. Let me see. No comments in chat. Okay, so any comments, write in the chat. So now I will open the task and give you the template and explain it, and then we will code the vanilla RNN, and it will become much more clearer soon as you will see the code, hopefully. And then you will have opportunities to build more advanced models, and basically there's lots of things you can work in the future with also RNNs. RNNs can be combined with many other things and can be used as classifiers, as modelers, and all sorts of things. So let me add. They can be used in autoregressive manner, in just like one go manner. There's lots of ways. Just a second. So where is my task? Where is my task? Implement vanilla RNN with the template. I have it here. So this is the series. So I hope this is the 11th series. Okay, cool. Yep, so we have already survived to the 11th tutorial of AI tasks, basically. You will have normally this course become like contains even more lectures, but probably till the new year we will get to the transformers and maybe to reinforcement learning a little bit, but not more. So if you are interested on continuing learning all of these things, I definitely have more materials, more courses, so please connect me and also we can do research together. So I opened this new task. Please go there, pick the template, and I will show you the template. So the template. Oh, this is not the template. This is the template. Okay, cool. So what we have here, hopefully everything will run for me. Sorry. So here, this is important actually. Hopefully you remember that. If you have GPU on your computer that is supporting CUDA, then in that case, if you have GPU that's supporting CUDA, I highly recommend for you to comment out these lines for you to be able to debug the code, because these lines just mean that please give me 200 samples of the dataset because I'm running on CPU. If I'm running on CUDA, then I want to run all of the samples, okay? Dataset. This is a quotes dataset with all sorts of famous people quotes, and I'm loading it like this. I have the final quote sentences, final authors, categories, vocabulary keys, vocabulary counts. Vocabulary keys means there is the words in vocabulary and how many times these words have been used. Authors categories. You can actually make the model much more fun if you could embed and include in the prediction also the embeddings of categories and authors. Then you will have, for example, humorous quotes, or the fictional quotes, or non-fictional quotes, or business quotes, or so on. So this would be really interesting experiment. Then you also have max sentence length. Even though LSTM do not and the RNN do not have limits on max length, we still need max length because I want to construct these matrices, right? Remember the matrices? Let me show you. So these white box, so all of this maximum length box, if I don't know what is my maximum length, normally I would calculate maximum length for batch, but for simplicity reasons we can calculate it for the whole data set, then I would not be able to create this properly. So that's why I need the max length. But there is no limit in inference how long sequences we can generate. So then what else? We also, by the way, we will also have the token, the specific embedding for the end of sentence so that we know when to stop generating sentence. Then we have get item. In the get item, what I want is to create this shift. So I have two sets of sentences, but one set is slightly shifted to the left, right, by one time step, because we will predict each next time step, right, for the training. Okay, so that's that. I will, in a second, I will add a breakpoint and give you examples how these sentences looks like. So then there is a training and testing loaders. Then there is RNN architecture that we will implement. There is this thing called packed sequence. Packed sequence is this format that is used in PyTorch to deal exactly with this situation. So to deal with this situation, you use packed sequence because you can store your data actually as a long sausage, basically. So if you imagine that this is definitely not optimal way to store your data, right, with lots of zeros, right? Not good idea at all. So, but what is good idea is if you could store data in this manner. So this is one-dimensional data, like a sausage, right? And then I store this part, I store this part, and then I store that part, right? You can imagine that you can store it in one dimension like long sausage, right? But then you need also to store what is the ends on each sentence, right? So if I store where the sausage are cut, then I'm able to use this data format, right? This is packed sequence. Then what else? Then we have loss of weight. So this is also important to enforce the weights of the tokens. Then then we have all of these accuracy calculations. We want to predict how often the same precise word is predicted in these known quotes. And finally, at the end, we can roll out or generate some quotes ourselves, right? So we will just take so this means just take no, this not, but this one, just take the first word of so take first word of quote, any quote that is given there in this last test batch. I wrote it right, quote, oh man, and generate rest, right? So this is what we are doing there. And the generation part is this one. So we're just the key thing to understand here is that we're just taking the last token, just using last word and memory, basically, and memory. We are not feeding all of the words when we are using this in production. So let me go back here. So here, this would be basically this is kind of the correct way. So we can just predict continuously ahead without feeding back the previous words. So that's what we're doing there. Okay, so there's a lot of things you can do with RNNs. They're pretty cool. So now let me show you a little bit of dataset. So if I'm making a breakpoint here maybe, and hopefully we'll run this file. So debug until download dataset probably. Hopefully it takes not so much time. Okay, where is the okay download URL? Oh, it's taking a little bit too much time to starting up. Not sure why it's taking so much time. But while it's loading, we can maybe start coding something. So I will show you how the data work when this finally loads. Really confused why it takes so long time. Okay, if I close this thing. Okay. Sorry for my cough. It's really bad right now. Okay, the create connection. Something is not wrong with connection. Whoa, that's not cool. Let me know if you can download dataset. Hopefully the dataset downloading works. You can actually use HTTPS as well. This is strange. Let me check. Hopefully my server is not down. It should be very sad actually. My server is down. Okay, this is not good. For some reason I was not able to open my server when I tried at first time. Let me see if I can get to this. Let me double check. Please let me know in the chat. Did you able to download the dataset? You can try also HTTPS, by the way, here. Maybe that works. Okay, it's a little bit freezing my computer. So I really hope that my server is not down. Yeah. Okay, no, doesn't look good right now. Let me know in the chat. Did you manage to download the dataset? Maybe my internet connection is broken. Okay, let me ask in the chat. Uh, is so dataset download works for you or not? Oh man, some kind of strange stuff happening. So asking in the chat for help. Meanwhile, I'm looking what's happening with my server. I was not expecting this, of course. So just a second. Okay, it doesn't work. Okay, let me try to. Okay, I believe probably the server is down or my connection is down. Only two things can be right now situation. I'm trying to find. Okay, please answer in the chat if it's working or not working if you can. Um, Meanwhile, I will try to ask other people around what's happening. Mhm. So I'm waiting for your response in the chat. Also trying to ask other ones if somebody can test. Okay, nobody responding me in the chat, at least seems like. Hmm. Can you hear me? So how to test the download? You just need to run this code and it will go to this part and it will try to download dataset. By the way, if I will not resolve it quickly, I will just add my own dataset. Okay, not working. That's not good. Moodle, right? You cannot even get the template. Thank you very much for helping me. Okay, so this is not good. Okay, I need to ask things. What's happening? So just wait a second. I will get. Anyways, we can continue in the sense that. So first of all, I will share the template with you on the chat on some other channel. Plus also the dataset you will get a little bit later probably. So just bear with me a little bit. I need to check the connection. I was not expecting this, of course. Let me see. So Okay, let's resolve it one by one problems. So first of all, let me quickly give you the template somehow. So I will share it through some other means. Let me quickly share it. So file MLA, I guess. I will put this link in the chat. Okay, so cool. So problem one. So the template. So I give you the link in the chat to the file MLF with the template. Please get the template. You should have told me sooner that the template doesn't work because the server is down. So so that is one thing. Please get that one, and the other one is I need to somehow share you dataset. Let me try to find that one. Just a little bit. Wait, was not expecting this because the server worked just before, and now it does not work. Okay, I have quotes. So the quotes, the file which I will give you, yeah. So basically, you should uh, you should put that file inside data folder in the root directory. I will show you. So let me get that one also to you. It's a little bit complicated. Right. So how can I send another file? Just a second. File m.lv doesn't want me to send another file. Okay, we'll do this in the other way. Okay. Okay, I have it. Yes. Oh, you actually hope that the previous file worked because I did not press save. Let me check. So this will be a dataset. Dataset. So I shared in the chat two files. Hopefully the first one also is there. Yeah, it is. So you have everything that you need. So and the data set, so you need to put it in this directory. See, there are two dots. It means that this is not your current directory, but parent directory, and there should be data on quotes inside there. Okay, please try to do this. Hopefully now you have access to all of the files that you need. And meanwhile, I will run this code just for you to show what is inside the data, right? So now I'm trying to run it. Okay, now I got forward, but right, I know where the problem is because it started to train the stuff, but I don't want to train it, so just I will query the first array there, first element. Okay, now it will stop. Cool. Now it stops. Great. I will show you how this works. So just please get the data, get the file, which I showed you, and give me like 1 minute to now put you on mute, and I want to call my server guy about this because I don't like that server's down, okay? And I will show you just in a second what is inside, and we will finish this tutorial. Okay, good. Server guy told that yes, everything is broken, but he is fixing it. Okay, that's not of course great news, but that's what we have right now. Actually, I just realized that probably my Moodle is down as well, right? Moodle, Moodle, Yellow Robot, right? Everything is down, right? It was not down when we started the session, so unfortunately, let's live with what we have. But it will be up soon because this is just a network connection error. So let me show you what it is. So here is the getting item. So now we're trying to get one quote here, and what is inside this these quotes. So let me show you. So the if I'm just right now looking at so X row. So this is the row numbers here. These are the identifiers of the words basically. So we have these identifiers of the words, and then we have the vocabulary keys. So by the way, by this point, I really hope that all of you got the code because I shared it in the chat with the file MLV. So here the keys. So if I'm now write the key number 50 basically, you see that I get the word don't. And if I write the key number 792, then I get the word cry, don't cry, basically. So, and what we can do, we can do better. We can actually make some kind of output here. So this will be something like this, so that I would, if I want to see what is the sentence, right? So if I want to see what is the sentence, I would write something like this: join this by IT, the iterator for IT in the X row. And now don't cry because it's over, smile because it happened. And at the end there is this end of sentence token. So this is basically what is in the dataset. There are these small sentences, the quotes of famous people, and they are encoded in this manner, basically. By the way, let me know in the chat. Actually, I will ask. So, did you get template and data? You get template and data. Let me know in the chat. So that's that. And then let's keep digging. So this is then the okay. So this will be the quotes. And then if I want to know, for example, which author wrote this quote, so if this is index 0, I can just look at there. This will give me author 81. And what is the author? There is author keys. So this quote is done by Dr. Seuss, basically. So, and you can do the same for any inputs, right? And we can even check what is the category of this quote. Like this will be quote, don't cry, it's already be happy when it's happened. And the category of this quote is life. So this is how you operate these language datasets, right? So this is our small language dataset. Then what we need to do here is to do visually, I can show you is exactly, where was that slide? So this thing, we need to make sure that our sentence, the same sentence is rolled in that direction. So there is a what here, first word, right? Which is then deleted, right? And we will predict from the first word, the second word, basically. And then from the second word, the third word, and so on. So this is our task. And we do this because I explained that the gradient flows way, way better if we do this rather than try to just predict one word or something. So this is that part. I don't see in the chat that you confirm that you got the data. Hopefully you got, because I sent the links to those data sets and columns and the template. So please let me know. So here, anyways, if you have any questions so far and so on, please let me know. We'll start trying to make the equations reality in the code. Oh, something is broken. It's not writing anything. For some reason, I did something wrong here. Not sure. Just a second. Meanwhile, you have a time to try to access the template. So okay, I think my PyTorch just went out. I mean PyCharm. Oh no. Yeah, now it works. Okay, cool. For some moment, my keyboard was not working. Okay, cool. So we're back. Okay, so how we do this? We are at the line 65, and what we want to do is we want ground truth inputs, which are rolled or shifted on the left by one word. And how we can do this is np roll. And by the way, roll function is tricky function. I will explain. So roll function actually will not remove the first word. It will move the whole array, basically uh, shift around. So what it means is if before I had something like this, so 1, 2, 2, 3, for example, 4, okay, right? After this call, I will have 2, 3, 4, and the 1 goes at the end. So this is what happens. Then, if the 1 goes at the end, I need to cut the 1 that goes to the end. So what I do, I cut the last word, and I can do like that. And when I do that, the output will be like that, right? So this is my target words, right? So then the input words, I also actually need to cut by the last word, because the last word will be actually predicted one, right? So I want to predict the last word, not to give the last word to the model. So this will be x row cut the same way, but the output will be different. The output will be like that, right? So the input will be 1, the output will be 2. The input will be 2, the output will be 3, and so on. So that's that. Then next thing is the length of this thing. So this will be len of what x, because there will be different length sentences. Okay. Then, as you see, the output should be padded. And this is what I talked before. Again, we need this kind of format where we have all of the sentences the same length. And when I do the batch, I need to make sure that this is the case. Oh. And to do that, let's do this. So pad right. This is not the only way how to do this, by the way, because we could actually use collate function inside the torch utils dataset to be basically optimal, so that we don't have always the maximal sentence length, but only the maximal sentence length of the batch. But in this case, we don't want, oh, sorry, the collate function is actually in the this one, where is it, data loader. So here is the, if you would like to do it optimally, you would write here collate function, and this would then do the paddings separately. But now let's make it the most simplest way. This will be the same paddings for the whole dataset. So it will always be the same size matrix. So here will be x padded and np pad x. So we will pad x array by 0 on the left, and pad right on the right. And the same for y. Make sure you change exactly these letters here, otherwise you might have problems. So adding this to the whiteboard. So this is the dataset preparation. Eventually, this is the way how you will prepare your dataset for all of the language modeling tasks. Even ChatGPT type of tasks, basically language modeling using transformers, also goes through the same process. The then the next step. So the next step will be the model itself. But for the model, let me think. So we will have the inputs. Inputs will be indexes. We need to change them to the embeddings, basically. Huh. So how we could do it better? So let's just write the RNN equation first, and then we will do the model part with embeddings as well. So how to do the RNN function? So let me go back to the function. So this is in the first slide. This is vanilla RNN function, and let's implement it together here in this code. Okay. So I know my Moodle is not working, Rainy, but I gave you now the two links in the chat where you can get the template and data. If you do take them, you can finish tutorial with us. The Moodle and file systems will be up and running a little bit later because something happened with network connection on server. Okay, so that's that. Let's keep working together with what we have. Right, I gave you the templates in the chat. So here, let's use the exact same notation of the naming, okay? So there will be self wx. This will be torch and n parameter. There will be torch float tensor, and there. What I'm now doing, I'm creating the default value, and the default value will be embedding size times the RNN hidden size, and let's uniformly initiate from -1 to 1. Let's double check if I'm using the 10H. Is that a good idea? Let me go back and see. Sorry for my cough. So -1 to 1, it's actually, so the range is, I think, okay. Like if we go like -5 to 5, then it's already dead. So, but -1 to 1, I think it's okay. So yeah, so that range will be okay. So then the same thing for H. Okay. Oh, H. So this is the hidden. And then the similar thing to the B, because this is bias, right? And this is BH, the same of the, oh, yeah, so the for the bias, but I think there is a bug here. Let me look. So the hidden size will be hidden size, so it should be like that. The we will, or maybe not. Let me check again the equation. So WH, no, this must be hidden size. Yep. So there is like that. And the last one, the float tensor here, this should be like just RNN hidden size. Remember to add here a comma, because this comma is very important. It will make that this is a tuple, and all of the hiddens are usually zeros. By the way, if I'm not defining these initial data values, then these vectors will be kind of random, because they will be, but they will not be uniformly random. They will be just random memory space. So now, how to make this work? It's very hard for me to talk a little bit. Let's get through this tutorial because this is important. So X unpacked. So we will get this packed sequence. The packed sequence is the sausage format which I told you. Okay. So let's create back from sausage format into the matrix format. This will be unpacked X lengths, pad. By the way, these RNN layers can be stacked on each other, so that the outputs from the first layer can go to the second layer. But we can talk about that later. So packed pad sequence and the batch first. This is important. By default, everything is actually batch first false, because the optimal way how to store data is to make sure that the sequence length is sequence is the first, because then the for loop is better. But you will see in a second. So normally all of these RNN cells, they have the input of hidden. This is my memory. I can pass the memory from output or from previous layers. But if it's not passed, I can define it myself. So is none, then let's define this hidden layer. So there is a little bit of trick here. Uh, so we need to know the batch size as well. So this will be the batch size coming from x unpacked size 0, because when we are running this in inference where we're generating the text from just one word, we might not have multiple samples at once, right? And we want this to be working, not having error. So torch float tensor batch size comma RNN hidden size initialize as 0. By the way, the fun thing that you can do, you can make the memory learnable, the initial memory. We can make it as a parameter actually. So that's also possible to do. So to device. So because if you're running on CUDA, you need to send to the right device. So that's that. Then next thing. So first of all of our sequences are coming into this format, which I said, batch sequence embedding size, okay. But I need to get this format in sequence, batch embedding size, because I want to for loop through this sequence, and this is important because of this. I want to go 1, 2, 3, and so on, okay. So what I need to do is to change the order of dimensions, and I can do this using the permute. Permute, let's go, first dimension goes, the second goes first, the previous first goes second, and the last goes last, okay. So then the next thing what we need to do is to accumulate all of our hidden outputs step by step. So what we can do is here to collect the outputs. So these will be outs, okay? Then we start doing the for loop. For xt, so this will be the each time step in x sequence, but now each xt will actually contain batch comma embedding size. Basically that is the what each time step will have. And now we will apply the equation basically. So the equation, maybe just to split it in some parts. So let's split it by, so this will be the y times y dot, let's say y dot x. So this will be that part. So to do this part, remember that if you don't know this part, you need to go back to the previous lectures, but the idea is that I want to make sure that I can do the dot product, this at sign, right? So do the dot product by last two dimensions, and right now I do not have last two dimensions. I have batch dimension. If I do the dot product by batch dimension, that's a very bad idea. So what I want to do is add extra dimension here, so that my two-dimensional algorithm called dot product works on these two dimensions. So that's why I'm doing some operations here, and my operations are following. I'm copying all dimensions from batch, copying all from the embedding, and adding the new dimension. So this notion means just add me new dimension. And then when I'm getting rid of that dimension, I'm saying all of batch, all of features, select me the first dimension. Okay, cool. So this is how you get the first multiplication. Then the second multiplication goes by h, and here we will use hidden. And one thing to notice here, this is not dependent on time. The hidden is always the same hidden vector used many times. So that is powerful and important. So, and then here you just apply the same equation which I have on the first slide, torch tan h of the, so what was the order there? So let's go back. So first is the h. It doesn't matter actually the order, but whatever. So f, wait, dot h plus, yeah, plus the other one, f dot y plus self bh. So that's what we have here. This is in a nutshell the equation. And for each time step, we will save what is the hidden value here. So these will be our outputs. Then let me think. So we are overriding these values here on this line. So this means these are not pointer. These are pointers, but these are not always the same value pointer. So this will be good. Okay, hopefully. Okay, so then we're adding them there. So then out sequence. So this, when we're getting all of these outs, right? These will be the hidden size outs. We need to make sure that they are back in the same shape. So torch stack out. And now what we're getting from these outs is the batch comma hidden size. Okay, and so yeah, sorry, batch, there's something off here. So no, this will be sequence batch hidden size like that, right? And now we need to change the order. So this will be out uh, torch permute or just the out sequence permute, and the same thing 0 2. And now the output is a batch sequence hidden. Okay, cool. So now we successfully implemented RNN cell. We just need to pack it back in this sausage format. So, and the sausage format looks like this: pack pad sequence, out sequence, x length, batch first true, and enforce sorted false, which is also very important, because normally all of these sausages must be sorted by the largest sequence first, but I don't have here the sorting, so this argument takes care of that. Okay, so let me add these lines of code to the whiteboard, and you will have the RNN ready for work. Then we will move to the next step, which is also very important, about the embeddings and the model itself. And then finally try to run it, and then I will give you some guidance regarding the other more advanced models that you should try yourself, basically. But this same equations goes, basically it's very similar. There's nothing much different. You just need to follow very carefully, add breakpoints, debug slowly, and you will be able to succeed with all these things. So let me see. Okay, good. Let me check in the chat. Mm, okay, nobody writes about the did you access the templates? It'd be nice if you give me some signal. Um, okay, we'll see. I think the network connection will come back tonight, probably. I don't think that a network company will let it down for too long. So then the next step. So this will be also very interesting in my opinion, because basically you will deal with these kind of ways how to work with these embeddings. So first of all, mm, so self, oh, and these will be the word embeddings, okay? So embedding, torch, and n embedding, and here we will have specific token for each of the words. In in more advanced models, actually, if you would try to use large language models, you would have something that is called tokenizer. Tokenizer helps to split your words into subsections and give these embeddings to these subsections, basically. And this is some statistical way how to do this. So, and now I'm just adding the maximum number of words that I have and embedding dimension. So all of my words now will have the same word embedding size. So then, next step, so I will define my RNN in the middle. And now I will just have one layer, but what I can do actually, if I want, I actually can do the torch and then modules or torch and then sequential and put together multiple layers on one on top of each other. Or I can also try, so what is the normal way how you would do this? You would use torch and then sequential, sequential. And in each of these torches and then sequentials, you would have multiple RNNs. You would have RNN1, RNN2, and these are the same cells what we did, but just stacked on each other. So the inputs now for the next one will be the input size would be the hidden size, right? Not the embedding size. And the first one would be inputs is the embedding size, basically. So this is the idea how to stack together multiple layers of RNN. But in our case, it might not be that simple because we have two outputs but one input, right? Oh, no, we have also two inputs. So maybe it works, but the problem is that I don't want to pass the same hidden vector to the next one as in first input. So the sequential for our models might not work as well. But in general, this is the way how to do this. And finally, we have fully connected layer, and today I already told you what it means because some of you might not remember it because you did not do it correctly in the last task, but I saw a lot of good things about the last task. So good job, people that you try to do your best. Many of you for the last task, again, please don't do these dummy things which other people do, because I believe most likely those students, some of them are foreign students that are doing this, which I showed you in the very beginning. They are just like not watching lectures at all, and they're just generating code and submitting it. So I just need to start giving 0 points for that. Maybe they will start watching lectures and hear that I'm saying not to do this. But anyway, so that's that. So yeah, so we just define the outputs, and outputs will be a softmax of all of those classes. There is an other way, better way how to do this. We will show you that in the next lecture. So the X embeddings now will be self embeddings forward, and now the sausage shines. So now I can use sausage feature X data, and X data is the sausage of these things. Let me show you. So all of these. So again, if some of you forgot what I mean, so I just connect in the sausage all of these things together, right? So, and this is X data basically. So maybe I should add here note so you know. So this sausage thing is X data. And then when we have these unpack sequences, we go back to this format. So this was the sausage. We are passing it through the embeddings, and now all of the indexes become embeddings, because before we had basically what we had, the X data is the basically batch times all of the sequences, so this will not be perfect, but one, right? And after this is the embeddings, okay? Embedding size. Cool. Then we need to pack it back. So we unpacked it, but we now need to get it back as the packed format. So this packing and unpacking is something you need to get used So packed, this is not nice code. If I would write this code for PyTorch library, I would make it nicer, but unfortunately they have it as it is. So X embedding, batch sizes, so X batch sizes, and sorted indexes, X sorted indexes. So these are these top indexes where we need to cut the sausage. Now comes the fun part. We just call the RNN. So out hidden equals self uh, RNN. Oh, sorry. So self RNN forward expect hidden. And again, hidden comes here as the none because we can define it as a memory for our generation, or just for the training purposes we want to have new memory for each sentence. So that is why it's none. So then logits. This is the outputs from the basically from the last fully connected layer that goes into softmax. So uh, forward out data, again sausage. Okay, then y prim torch softmax log its dimension, last dimension, so -1. And finally, we need to again to pack it back. And for the packing back, I will just copy this part of the code and change it. So this will be y prim packed, y prim, and the other parts actually don't change. So this is the model, basically. If you did not get along with my writing speed, you can catch up a little bit later. Hopefully the server will start working as well. Can roll back and do it slower, but just because we are running out of the time, we need to get somewhere, okay? So this is this. At least if you follow the code and write something, it should be at least enough to start understand what we're doing here. So this will be that. Okay, cool. So this is the model and the forward pass, okay? Good, so let's go down. What we have, okay, the loss weights. Loss weights we can implement in the way that I showed you, where it's 1 minus divided by sum, but this is actually not optimal because the difference between more often words and less often words will not be as dramatic. The way how I would recommend to do this is something along lines like this. Long, and then it's long but float tensor. And we could just divide by some division, like the most simplest one version would be 1 divided by np array of uh, dataset pool vocabulary counts. And this would mean basically, if we model it out a little bit, what it happens is if I divide 1 by some word which is very, very often found, like this would be word de, for example, de, then my weight for de would be basically something like this. So this is e minus so 1 e minus 5, right? So this is the basically weight for word de, right? Or c de, basically, in that equation, okay? And if I have some word like electricity, which is a rare word, it is not used often, right? Maybe, probably this is wrong spelled, whatever. So anyway, so this will be used 100 times, right? So this should be now much by the order much higher gradient. So e minus 2, basically. So here is this is 5, right? So this is like yeah, so the the this is like common way how you scale the classes actually, and I think we talked about it already. And if I want to smooth it out, don't want to be as aggressive, I can just add here a little bit higher coefficient, right? Like 100, for example, and then it will be something in between. But the formula which I gave you in the task, it's also not wrong, but only this is kind of not powerful enough to take in account exponential differences. So finally, we need to go to the last step of the training. The step of the training also is not that difficult. So we pad sequences again, the same old function. Make it in this sausage format because the batch so the data loader will give the matrix format, but I want this sausage format. So this is the X, then we need to do the same for the Y. Same for the Y. And what else? We need a loss function. The loss function is actually quite simple because this is just regular CCA loss, the cross entropy, so torch logarithm. Oh no, torch mean first. Torch mean. And I already gave you the class indexes. The class indexes are actually quite important. So loss weights, and here, if this is in this format, indexes y, it will take weight for each of the specific word, like the electricity and so on, and this will multiply it here by the loss itself. So what it means is that rarer words, like words that are not as often found, will be more important for learning than words that are found very often. That's one. Then also here the y prim packed data. I will again use this notion of indexes batch. So it is just a range 0, 1, 2, 3 selector, and here I will select the right indexes from there. So if you did not see this kind of notation before, this is very common notation to avoid. So this is actually exactly the same as y logarithm of y prim, but instead of having here the one hot encoded vector in front, it is moved here because this is just basically the same thing as selecting the index from the array. So that's that, plus e minus 8. And finally, the accuracy calculation. Accuracy calculation is exactly the same as for all of the other tasks that we did before. So it is a mean of index matching. Indexes of y prime equals indexes of y, and then multiply it by 1 to make it that where it's not matching it's 0, where it's matching it's 1. So I believe that's it. Hopefully that's it for this template. Let me check. So let me add it here to the slide 12. Try to run it. We'll try to make it also work on Google Colab in a second. So let me try to run it in demo mode and then also in the live mode. Oh, but I will not be able to run it in live mode if my server is down. Oh, there's also a bug. I will fix the bug, no worries. But at least in demo mode, I will be able to run it. Hopefully, if my server is not yet up. So, what is the bug? Not defined. Oh, there should be xlan. Sorry, there is a bug here, and here also should be xlan. So this is one bug. sometimes when I'm doing these tutorials in live, it's great that people can also help to find bugs before I test. So this is really cool experience that, you know, a lot of people are looking in the same code and making the best of it. So now, yeah, so it's now training and it's generating some nonsense basically, because initially it will always generate nonsense, but as soon as it starts training more, it will get higher accuracy and you will get more sensical quotes basically. And also remember that right now I'm not running it on GPU, I'm running it on CPU here. And if you would run this on GPU, you would use the whole dataset. Now I'm just using some part of it. Also, I don't like that it's not actually on right. I don't like one thing. Let me actually fix this and I will help you for you as well. I made this as an interactive plot. So please don't make it as interactive plots. That's my own fault here. But if they are not interactive plots, then they will show up like separate images, right? So let's try to fix up this. So I will remove this one, and here I believe I should add plot show, not plot draw, but plot show, and don't use plot pause. Basically, if you remove these parts, then this will behave more like other templates before. I accidentally made it with this interactive plot. Interactive plots not always work nice with Python. So let's try again. Let me check in the chat if you're still alive. I just want to give you some more guidance a little bit, and then we'll wrap up for the day. Again, remember that okay, hopefully it will. So every 10th epoch something should appear. Okay, we have something. I don't see any line there for some reason. Maybe the lines are not stored. I don't know, something strange is happening. Need to check, but I want to give you more guidance to some other things. So losses append, it should work. I'm not sure why it's not showing up properly. Oh, 10 epochs or true. So this means show every epoch actually. Could delete that. Maybe the plot will clear. Maybe that is the problem. No, that's not the problem. I think. All right, this is the problem. Figure subplots. I need to move this down here. Yeah, now it will work. So now you will see plots happening. Okay, but I want to show you just a few small things and then we'll wrap up for today, but hopefully you will see that this is valuable. You can try out yourself, run on GPUs, and you'll have quote generation model, right? You can generate, for example, also if you want bit something, right? So this is the plots. But of course, if you're trying to generate something which is unpredictable, don't expect really great results. So, but I want to end up with couple of very important aspects. So the homeworks for you will actually involve a little bit more complicated equations, but not much more complicated equations. So basically, you would have GRU and LSTM units that you can implement. I just want to show you how these units look like a little bit. So do I have somewhere that equation? I believe I do have it. Unfortunately, it was not. Oh, it is under that server. So unfortunately, some things already are on the server, which I cannot access right now, which is funny. I was not expecting that, but let me find. Do I have some GRU unit? I think I only have LSTM unit image right now, but you can find it later as well. So this is how the LSTM unit would look like. Oh, let me see. Can I? Oh no, I actually so right because of my servers down. Okay. Uh, okay. Still, we are good. We are good. So the LSTM unit looks something like this. The one which I will give you is more simpler one. It's you don't start with that complex. But the idea is that instead of having just this vanilla layer, right? Vanilla RNN, you could have something like this, and this is actually very cool. Let me explain why. So you would have multiple gates, so to say. And gates, what I mean by gates, it is like a quote-unquote metaphor because the sigmoid is always from 0 to 1, right? You see there is a sigmoid, sigma functions, right? And these sigma functions serve as gates because this always will be from 0 till 1, okay? And then you will have the same equation as vanilla RNN, but what you will have is that you will have the different behaviors. So you will have forget gate, so you will be able to forget the memory. You will have input gate, so you will be able to understand how much input should I want to pass in, and so on. So, and there is internal gate, output gate, and then you produce the output in this manner. So the only difference from this equation and what I showed you before is that you need to go here in the code and you need to add more learnable parameters. You will have not only 3 here, you will have, let's say, 9 or more, yeah? And you need to change these lines, and that's it, basically. Even though this looks scary, it's actually not difficult at all if you just implement this equation. So this is one thing. Then, mm, then, basically, I want to show you a couple of more tricks. So if you want that every time the model predicts different output, because now it will predict the same quote every time, you can add the dropouts, and dropouts are just these random layers which replace inputs to zeros, right? Basically, you could add dropout, and this is torch, and then dropout function in between layers, and it randomly will, let's say, with 50% chance replace your sum of your matrix values as zeros. And this is normally used actually for stabilization, so it makes more robust models. But it can also be used for language model really nicely, because then every time when I run my model, I will get different outputs. And this is the same as temperature for the ChatGPT and so on. Drop out, and you can add these dropout layers anywhere you want. If you want the model to be even better, then instead of having the fully connected layer at the end, you could have something like this. So this is even better architecture. So in this architecture, you would have the same embedding that you added in the front, the embedding layer, but this is transposed, right? If you transpose it, you can get out the same output. So in the for each word you would have once use the embedding and then transpose the embedding again. And here is the dropouts, by the way. So if you build this architecture, you will get really nice quotes generated. So finally, I want to give you one more thing, which is very important, is that you can use RNNs not only for generation tasks, but also for classification tasks and for like this. So what it means is that I can get all of these predicted outputs for each step, and I can do, for example, average pooling, right? Like I could just literally do the one-dimensional average pooling. So here, so this would be average pool 1D, right? Or mean, like this is average pool or max pool, and then I get just H value, like actually just very small vector, which I then can use as a classifier head. And this is super powerful because what you can do is not only classify, which you can actually also do, you can actually select only this guy and send it to the classification, or you combine it together here with torch cat, these two sides, and you can make it even more powerful model. So like torch cat, and combine these two vectors and pass it to the classification. So this is the way, for example, you have inputs of the sensor readings. For example, there is a feed of water sensor readings, and I want to detect if my water is contaminated or polluted, right? It will give me the if this is a clean water or not drinkable water. And this will not predict the sensor readings of the water directly, but it would predict me yes or no, basically. So these models are very powerful. So I hopefully I gave you some insight of this, and please try to do these homeworks yourself. If it doesn't work for you, it's okay. We can look at the code, but it's better than just generating something or just copying from others. But I believe you guys who are listening and watching this, you probably are the good ones, and those who are submitting all of this trash are probably those who even don't watch videos. So let's see you in next lecture. I will try to make it in between the holidays, right, in between the Christmas. And next time we will look at proper transformer architectures, like attention is all you need, basically. So, and that will be something also very valuable for your own benefit. So, please keep me, please contact me if you see that you're getting along. I see some people are, and if you want to do more research with me or basically learn more of these things, because the course will end soon, but I'm happy to assist to learn to help you learn more, and and then remember about exam dates, okay? So exam dates also, please vote for them. So that's about it for today, okay? Hopefully my internet connection actually was stable.